The topic for today's video is about sequence. Now in this video, I'm going to define a sequence in terms of a set of numbers and in terms of a function. First, let me define it as a set of numbers. So we have here, a sequence is a set of numbers, u sub 1, u sub 2, u sub 3, and so on, in a definite order of arrangement. Means correspondence with the natural numbers and formed according to a definite rule. Each number in the sequence is called a term, say u sub n, and this u sub n is called the nth term. Now the sequence is called finite if there are a finite number of terms. Otherwise, the sequence is called infinite. So we have here the notation for the sequence. This one, sequence, denoted by this one or this or as this. So let me consider here an example. We have 2, 7, 12, 17, up to 32. So 2 here is the first term in the sequence, followed by 7. This is the second term, or this is our 2 is u sub 1. This is u sub 2. Here u sub 3. This is u sub 4, and so on. So this is our u sub n, or we will try to find out what is the last term of this sequence. Now, what is this sequence? Is this finite or infinite? So based from our definition, because there are a finite number of terms, it means that this sequence is finite. Okay, now let us try to find the formula of this sequence. Recall that the nth term of the sequence is equal to this formula, u sub 1. This is u sub 1 plus d times n minus 1. Where u sub 1 here is the first term, d is the difference or the common if we are going to subtract the two consecutive terms, then n minus 1. So in this sequence, u sub 1 is 2, and the difference is, of course, difference of 7 minus 2 is 5. 12 minus 7 is still 5. 17 minus 12 is 5. So D is 5. Therefore, our u sub n, the formula, or the nth term, can be written as 2 plus 5 times n minus 1. Where n is up to where? So n is where n is from 1 to up to, this is 7. You can check it. So we have here, if n is 7, we have 7 minus 1 is 6 times 5, 30 plus 2. We have 32. So this is u sub 7, the 7th term. Okay, let us consider another example here. So we have 1, 2, 4, 8, 16. So again, we have here 1 is our first term. This is our second term, third term, and so on. So this sequence is infinite. So it has infinite number of terms. Now to find the nth term of this sequence, notice that our previous example, that is an arithmetic sequence wherein we get the common difference between the difference of two consecutive terms. Now in this case, this sequence is the geometric sequence. So we will get the common ratio. Now recall that the formula to find the nth term of this sequence, for the geometric sequence, we have u sub n is equal to the first term times the common ratio raised to n minus 1. So r here is the common ratio. Common ratio between the two consecutive terms. So it means we are going to divide the two consecutive terms. Then common number there is the common ratio, which is r. So u sub 1 here is, the first term is 1, and then the common ratio is what? So 2 divided by 2, 1 rather, 2 divided by 1 is 2. We have 4 divided by 2 is 2. 8 divided by 4 is 2. So r here is 2. So we have 2 raised to n minus 1. Therefore, our u sub n is 2 raised to n minus 1. Okay, so where n here is the set of natural numbers. So let's try to check. If n is 1, so u sub 1, the first term is 2 raised to 1 minus 1 is of course 2 raised to 0, which is equal to 1. Now if n, say for example, is 3, then the third term of the sequence is 2 raised to 3 minus 1, using this formula here. So this is 2 squared, which is equal to 4. It means the third term is 4. So that's it. Okay. Now, when can you say that the sequence is bounded? So of course, a sequence is bounded if it has upper bounds and lower bounds. Now for an upper bound m, we have denoted that one as big M. This big M is greater than or equal to any term in the sequence. So we have here our big M here. It could be equal to the sequence or greater than that number. So this is what we call the upper bound, or we have the upper bounds of the sequence. It means if the sequence has an upper bound, the sequence is bounded above. Now for the lower bound, we denote that one as small m. So for small m, as you can see in this figure here, the value here, the numbers here are smaller than the given sequence, or it could be equal up to here only, or less than the value of the given sequence. So if the sequence has lower bounds, it means the sequence is bounded below. So if the sequence is bounded above and bounded below, we call the sequence bounded. So let's try to consider an example here. So consider this sequence here. We have the elements 1, 1/2, 1/3, 1/4, and so on. So if you're going to plot that one in the real number line, we have this sequence. As you can see, the terms of the sequence approach to 0. So does this sequence has an upper bound? So notice that the largest number in the sequence is 1. So beyond this 1 is not anymore part of the sequence. So therefore, the sequence is bounded above. It means m na to is greater than or equal to 1 m. So these are our upper bounds here. Then for the lower bounds of the sequence, Since the terms of the sequence approach to 0, so 0, less than or equal to 0 are all lower bounds. So we have here our m, small m, is of course less than or equal to 0. So these are our lower bounds of the sequence. So the sequence is bounded above and bounded below. Therefore, our sequence is bounded. Follow? If you use the definition of bounded above, take note that u sub n here is less than or equal to m. Why? Because m nato is greater than or equal to 1, and of course, ang sequence nato is up to 1 only. Follow? So, u sub n is less than or equal to m, because m is greater than or equal to 1. And then for our lower bound, so u sub n is greater than or equal to small m. This is our lower bound. As you can see, we have here our sequence. So m is on the left of the terms in the sequence. So u sub n is greater than or equal to m, because small m is less than or equal to 0. So that's it.